show you the collect notebook here. You can open this collect notebook. Okay. Then as usual, after you get your collect notebook, you have to create a copy in your drive. Save a copy in drive. So today we are going to do the deep learning neural network. We are going to build a neural network, which is going to be your first neural network, right? You have never built any deep learning model before, am I right? Yes. Okay, so after you have created a copy, you can rename it so you can find it easily. So maybe semi copy of this thing. So you can rename your notebook. And I am sure you all know how to use the notebook after Calvin's session yesterday. So I will do some introduction first. So today's notebook is brought to you by Red Dragon AI, which is a startup company from Singapore. So this practical workshop today is based on their workshop. Yes. So today we will move on to building a deep learning model. So first of all, are you all ready? Have your notebook ready side by side with you? Yes. Okay. So we are going to import the libraries. Every time before you build your model, you have to import your libraries. So I have already written here, this is matplotlib, NumPy, and also TensorFlow. Okay. So for neural network, it's a bit special because we will need to use the API on top of TensorFlow, which is Keras. So you have to write import TensorFlow.keras.models, import the model. Okay, and then you move on to another Keras API, which is the layers. So after you have your model, you will need to have your layer. I'm sorry, it's from, my bad, from TensorFlow Keras layer. Okay, you import the layers. So what layer do we have? We have the dense layer, which is also the hidden layer in between. And we also have the input layer. So we will need the model, dense layer, and input layer. Next, from TensorFlow again, so you can just copy this. Okay, but this time we need to use the optimizer. So in deep learning, we will need to have optimizer. So the optimizer we are going to use today is the SGD optimizer, stochastic gradient descent optimizer. So up until here, are you all okay? Yes. You can add a comment here. This is to import the libraries for the neural network, because we are trying to have the model, input layer, dense layer, and also the optimizer. And then lastly,
but where's the notebook for today?
Oh, I sent you the link. Let me resend the link in the chat box. And then you create your copy. I think I will send you the code here so you don't have to type it out since you left out. I'll give you a moment to open your notebook, Howard.
Okay, done. Thank you.
Welcome. So good. Now the last thing you need to import for the library is from TensorFlow, Keras again. Is the utils library. You need to import a plot model so we can plot a model later. I will show you what you will need to do with this. So the main difference between a machine learning model and this deep neural network that we are building today is that we have this thing. We are trying to have the model, the dense layer, the input layer, and also the optimizer SGD. Yes. So for today's session, we are going to deal with a data set called the MNIST data set. So what is this MNIST data set? I have given you the Wikipedia down here, so you can read more about it. But basically, this MNIST data set is a data set of handwritten digits. So you can see all these are handwritings, right? Human handwriting. So we are trying to let the machine learn from this data set to see whether this is a 0 or is it a 2 or is it a 6 or is it a 8. So you can see this 2 may look like a 1 and this 4 may look like some other numbers. So we are trying to make it readable to the machine because you all know, right? Different people got different handwriting. Okay, so this data set is really interesting. You can read more about it in the Wikipedia. So before we start building any model, like Calvin said yesterday, we need to split our data. So splitting our data, we need to split into two things, which is the training data set and also the test data set. So can I ask you, do you know what is the difference between training data set and test data set? Anyone can tell me? No?
Training is like to put inside the model, then to get the figure, then for the testing, you will put it to see the accuracy. Is it something like that?
Yes, you are right, Howard, you are right. So for the training, as the word imply, right, we need to give this model a training data. So in order this machine can learn from this data. And after learning, you need to give it a test, an exam, right? So we need to test whether this model is accurate or not. That is when we will use the test. Alright, Howard. So next we will move on to X and Y. So before I actually move on to the coding part, I need you to know what is the difference between X and Y. So from yesterday's session, you have known that X is the input and Y is the output. So this is like a variable, like Calvin said yesterday, variable. So X is the question that we are giving to the machine, and then Y is the answers to the question. So in this case, what is our X? Our X is this data set, the images of this 0 to 9 numbers. And then the Y is the label. So example, the picture 0 is the input, X, and then the label to this picture is Y. Okay? You will understand later. So right here, we need to import our data set. So how do you import? This MNIST data set is built in under the Curls API. So again, we will use from TensorFlow .curls .dataset import MNIST. Okay? And then you need to split the data, put a bracket, X train, Y train, and then comma, X test, Y test, the test data set equals to MNIST, this one we imported earlier, dot load the data, parentheses. So this is how you split your data set. You import the MNIST and then you split into S train, Y train, S test, and Y test, load the data. Okay? Okay. So I forgot to run. So you run your library to import your library. Okay, this might take a while. Okay, you imported your libraries. And then we will import the data set. You see, it is saying here, downloading data from this place. So now after you have imported, yes.
Okay, I want to add on something. Okay, so you guys might ask like why yesterday we have to, we import the X and Y from a data set and then we split it using another method, right? But then for this part, we can straight import from a data set and then get X train, Y train, S test, Y test. It's because it's all come back to the function itself. Yeah, that's why I say if you check documentation, you can see what is going to be returned. Yeah, so yeah. Okay.
Yes, so based on this MNIST, you can just import and split on the spot. Yeah. So after you have imported the data set, you want to take a look at your data set, right? You need to know what data set you have you have actually imported. So for the training data, you click, you write print strain dot shape to look at the amount of data you have, and then print train and dot shape. And then after that, for the test set, you do the same thing. You just copy, but you change the train into test. Yes, so you run the code. Okay, so after this, you have to see this is the train data set and this is the test data set. So from this MNIST data set of handwritten digits, there is 60,000 data set. That means 60,000 examples of these handwritten digits. And we have 10,000 examples for the test data set. So we use 60,000 examples to train the model, and then 10. So you can see what is this 28 over here. This 28 over here is to say that each of this handwritten digit is the size of 28 by 28 pixel size. This is the size of the image right here. Okay. So next, we want to take a look at our image, right? So I have placed this image right here before the workshop. So I thought maybe some people may not understand what is array, but I know everyone here understood what is array, right? Yes, you know what is array. Array is from an index of 0 to whatever size the array is. So let's take a look at our first image of our data set. So you know strain is the data set. So we look at index 0. We will run this code. Index 0, that means our first image, okay? So you can see in our first image, it is a multi-dimensional array format. You can see this is one image. So this image is all numbers. So like if we as human, we look at this, right? You don't know what number is this. Can you tell me what number is this? Do you know what digit is this? You don't know. Okay. So you can see this is a multi-dimensional array. And what are the values? From 0 to, do you know what is the maximum value here? 0 to 255. Okay. So 0 to, 254. 254 is the maximum. Yeah, so this is the multi-dimensional array of our first image. So you don't know what is this image, right? So we need to look at the corresponding label, which is the answer to this first image. So how do you get your answer? Not X, Y train, index 0. So like I said, X is the image, Y is the answer. So it gives you 5. That means this entire multi-dimensional array thing is the image of the number 5. Okay? Okay. So after that, you have take a look at our data set. We will now move on to pre-processing. We want to process this data. So from yesterday's session in our deep learning slides, there is one part where I said you have to flatten your image, right? So this image is a 28 by 28 pixel. That means we have 28 here and 28 here. So we need to flatten it. So when we flatten it, it is 28 times 28, which is 784. Okay, so we want to flatten the image. So how do we flatten the image? We need to reshape our data set. So we need to flatten the image. So this is called flattening right here. Okay, so how do you flatten? For the X train, equal to X train dot reshape. We use the function reshape. Reshape 60,000 of our data set into the size of 784. You see just now, right? This is 28 by 28, right? But now we don't want, we want 784, which is 28 times 28. So we flatten the image. We copy this line again, and we do the same for our test data set. Test data set. Okay. but our test data set only got 10,000 samples. So this is 60,000, 10,000, 784. Okay, up until here, you understood? We are flattening the images now. Yes. Okay, so after you flat the image, we want all this image and integers to be a floating point data type, so that we can do the calculation later when we standardize them. So because standardized is 0 to 1, it will have a lot of decimal number. We don't want the computer to round up into an integer. So we are trying to change them into a floating point max number. So how do you change it? You use the function, the method as type. So for the x training data, dot s train dot s type, we change it into float 32. Yes, float 32. And then you do the test data set. Just repeat for your test data set over here. Okay, so we have successfully converted them into this floating point. And then for this part, we are trying to see the shape and also the data type after we have put in this thing. So you run this code. Okay, see, after we reshape, it is now 784, and then it is a floating point number for both training and test samples. Okay, next, after you have converted them into, you flatten the image, you have make them into floating point, we are going to standardize this data. So from the image just now, you can see there is a number of 0 to 254. So we don't want it to have this much of a value here. We want to change all these into 0 and 1, 0 and 1. Okay, in between 0 to 1. Okay, so how do you standardize your test and training data set? So you can see here from this formula, our mean here is 0, and then max here is 255, and mean is also 0. So let's say x minus 0, you get x, and then 255 minus 0, you get 255. So basically, to standardize your data set, it is x train divided by 255.0. Okay, S test divide 255.0. So do you understand this part? We are standardizing our data to make the value into in between 0 to 1. So you run this code. Remember to only divide it once. Okay. So after you have standardized your data, you want to check what is our first image again. So S train index 0. You run it. Okay. So you can see just now we have a lot of values from 0 to 255, but now we have only values between 0 to 1. You can see all this is 0, and then some of it is 0 point blah blah blah, 0 point blah blah blah, 0 point something, and then 0 point blah blah blah, blah, blah like this. So it is between 0 to 1, right?
Sorry to interrupt.
Yes.
Sammy, I think you can put this code. Yep. np.separate option, so you can make this array looks like you can see the numbers itself inside the image. You just copy this code and then you just put on the print x. Yep. Yeah. Obey this np.separate option. Down here also can, up also can. Then you can see. Okay. Try running.
Oh, I need to print.
Yeah, print again. Yeah.
I didn't have the print here.
Yeah.
Okay. So what Calvin did is to make it horizontal.
Okay. I think like some mistake for this part. I think because we did flatten it, that's why I cannot see the number. Okay. So maybe you can just erase this and then go back to the first time we look the first image looks like. You got what I mean? Before you flatten it. The cell upper part. Yep. just to let them know that actually you can know the number. Yeah, this part. Yeah.
Oh,
Yeah.
okay.
Yeah. Because I see the array, go to another what I call that, another line. Yep. So just like this, then you can see actually the image can be.
Oh no,
Wait.
because I have already scaled the data. Hurry.
Oh yeah, that's true. I can never mind that. Okay. So like if you
Yeah.
haven't scaled, then yeah, then never mind. Actually no need. Just continue. Just to let you know that you can scale the print area. Yep. The layout of printing. Yeah, by using this number. Yep. Okay, so
Okay.
continue.
Okay, so after we have scaled the data, you can see now we have left with the numbers between 0 to 1. Okay, so no more 100 plus value or like 200 something. Okay, so same thing, we will look at the label. Is it still the number 5? Okay, is it still the number 5 after we have scaled the, oh sorry, not Y label, my bad, Y train. So we need to look at the label of this image. It is still a number 5, but then we have standardized the value from 0 to make it between 0 to 1. Yes. So something went wrong with this picture. Oops, not my snapcam. Snipping to. Okay, so from this image, do you have this image in your notebook? No? I think something went wrong with the image, but then this is the image that is supposed to be here. So this is, we are trying to do one hot encoding. Anyone here know what is one hot encoder? One hot encoding? No. Okay, so one hot encoder is, because, right, we have our label 5, or label 0, or label 2. So let's say this is not a handwritten digit data set. Let's say this is an image of a dress, an image of a shoe, image of a hat. So right, our label will be, this is a, actually not shoe, this is an apple, this is an banana, right? So we have all these label, this is the label right here. So computer cannot read this label, right? Because this is a alphabet thing, we need to change it into digit, okay? So from here, our data set here is written the label 5. Let's say we have a label 6, label 7, okay? So you can see 5 is larger than 6 and 6 is larger than 7. But then actually there is no meaning to this value here. 6 is larger than 5 means nothing. 7 is larger than 6 means nothing, because we are just trying to categorize this image into whether it is a 5 or is it 6 or is it a 7. So we are trying to encode these categories into numbers, okay? So you can say maybe for apple, I want to say apple can be 0, orange can be 1, banana can be 2, and then pineapple can be 3. But then this shows the machine that there is a meaning to it, 1 is larger than 0, 2 is larger than 1, 3 is larger than 2. There is a meaning to this value. So we don't want this to happen. So we use this thing called one hot encoder to encode these labels into an array, okay, an array of value. Right here, we are trying to have an array of value. So you can see, apple, I want it to be 0. Orange, I want it to be 1. Banana, I want it to be 2. So index 0, index 1, index 2. So I make this apple into an array, right, like this, into an array. So when I say this is an apple, all other value is 0 except for the first index value. All other value is 0 except for this, So we can see if this array 1, 0, 0, it will know this is an apple. 0, 1, 0, this is an orange. Banana is 0, 0, 1. Okay, so how come you may ask the array size, how do you know how much is the array size? You can see this is 3 categories here, right? Apple, orange, and banana. So we have 3 categories. So the array size is 3. we have 0, 1, 2. So let's say you have another thing called pineapple. So maybe we will have another 0 here. And then what will pineapple be? Can someone tell me? Hotwood?
0001.
Yes, you are right, Howard. Ziyi, good try. So for pineapple, it will be 0, 0, 0, 1. Okay, so this is how one hot encoding works. You can actually search up more on this thing. So the same thing for this thing, we are trying to make all our labels into an array of values. Okay, so how many categories do we have here? Can you tell me? How many categories we have? How many categories do we have? 10. Yes, you are right. We have 10, 0 to 9. So we need to identify 0 to 9. So we have 10 categories. So our array size will be 10. Number of classes is 10 right here. So we have 10. Okay, then we will use the two categorical method from Keras to change our Y train and also our Y test into. So Y just now, if you remember, is the label. So Y TensorFlow Keras dot utils dot to category to categorical the function Y train number of classes. We need to encode them into 10 classes right here, 10 classes. So the same thing happens to Y test. You change this into test. So this is encoding. You just run this cell. Okay, so you have successfully encoded this label into an array of values. So now you can take a look at our Y train, the first index. What is our label now? So if you remember what is our label just now, it is a 5, right? So what happened to the 5? So the 5 now is an array, 0, 0, 0, 0, 0, 1, and the rest is 0. So if you count 0, 1, 2, 3, 4, 5. Okay, this is a 5. So you have changed it into an array. So we can check the shape. What happened to the shape? The shape is now 10 because we have 10 different categories. Just now, right? It is just 1 here. Here it is just 1. It's not written. It's 1. So now we have 10 classes already. Right here we have 10. So after that, this one you can just run this cell to look at the digit. Okay. This is a 5. This is a 4, 1. So this is the example of our data set. So you might wonder, what data set am I dealing with? This is the plot example of our images. Okay. So until here, what we have done is that we have looked at our data set. We have seen value, and then we have flattened the image. So now it is time for us to build the network. We want to build the neural network model. So the first thing before you build any network, you need to have the network parameters. Okay, you need to define the parameters before building the model. So from yesterday's slide, if you remember, we have a lot of terms like this: learning rate, training epochs, batch size, and input layer, hidden layer, and also the output layer. So just if you remember from the slide yesterday, right, we have a 4 by 4 pixel image, and then we have 4 times 4, we have 16. That means we have 16 neurons. So in this case today, we have a 28 by 28 pixel image. So it is a 784 neurons. So for the first input layer, for the neural network, we need to have 784 neurons. So you define the input layer to be 784 layer of neuron. So the first layer of our neuron, we take half of the amount of our input layer. So half of 784 is 392. And then another half of 392 is around 100. It's something like this. This is a bit randomized. It's just something like that. And then for the number of classes, we have 10 class. Okay. So this is also the output layer. Like I said yesterday, the first input layer must be the value of the flattened image. And then the last layer must be the amount of categories you have. So for training parameters, we need to define the training rate. That means how big is the step the machine should do, one step at a time. We will make it into 0.01. So the next one is training epochs. We will have 10 epochs. That means the machine will go through this data set for 10 times. It will read through the whole data set for 10 times, 10 epochs. And then the batch size here is 100. We want to have a batch size of 100. That means in each batch, we will have 100 samples. So you run this thing to define the values. Okay. So after this, you have defined the values. We are going to build our first model. Yes, our first network. So how do you build your first network? You define input. So if you remember our neural network, we have input layer, hidden. So first thing first, input layer. So we will use the method input, and then the shape is 784. Okay, 784. And then name is, you can give it a name input like this. Okay, and then this is our layer. We name our layer as X is dense. So if you remember from our importing libraries, right, we have imported this input and the dense thing. Okay, so dense is the layer. So we have already defined the first hidden layer is called N layer -1. Okay, and then activation function. So for each layer, we need to have an activation function. Okay, the activation function we will use is the ReLU activation function, which is this one. And then we will have to give it a name. We call it dense 01. And then you put in an input here. So you need to connect the input with the layers, right? So you have to put your input here. This IMP. Okay, so you connect this input with X layer, and then you can copy this code. The next layer is the hidden number 2. We use the ReLU function also, dense layer 2. But then to continue this network, you need to connect. So the next thing here is X, right? This X we put into here, and then we got a new X. Okay, and then we will have the output. So for today, we will only be building a 2-layer model. So layer 1 and layer 2. And then outputs, we can make it into dense, number of classes, which is 10. And then the activation function for our output is the softmax function. And then we will have name. We will name it as a output. This is our outputs. And then we will connect it with the X here. So up until here, you understand? This is the input, layers, and then this is the output. Okay? Okay. So you might wonder, what is this activation function here? What is this activation function here? So you can see from this image down here, we need to go through activation function before we output it. So the ReLU function is a function where if the value given is negative, it will return 0. And values other than 0, it will return the same number. So if you give it 1, it will return you 1. Give it 2, it will return you 2. Give it 4, it will return you 4. So what is the function of this ReLU? Is that we don't want the model the neural network to give us a negative value. So any negative value, the function will return 0. Okay, so softmax function is a function where after it calculates the probabilities, right, it will choose only the highest probability and make it into 1. So from here, you can see the highest probability is 0.9, right? So after it goes through the softmax function, it will change it into 0, 1, 0, 0, 0. So it will know after this softmax function, it will know which one is the highest probability, and that is the chosen label. Okay, and then after this, we have built the model. Of course, we will need to have a model. Write your model here. You put in your input layer, and then you put in your output, and then you name it into basic MNIST model. So this is your MNIST model. You run this model. So it will take a moment. Yes. So we have input, layers, output, and our model ready. Okay, so now we have successfully built the model. You can read more about the function here. Okay, so now let's take a look at our model. You write model.summary. Okay, so this is our model. You can see this is the calculation it has done. 784 neurons, 300 neurons, 100 neurons, and 10 output here. So this is like a calculation. You can read more about summary. Okay, and then this is just the calculation that it has gone through. It will times with like the bias and everything. This is the math behind the neural network. You don't need to understand, but if you would like to know, you can click here and understand more about how the values are being calculated. Okay, this is like more advanced if you want to know the math behind it. Okay, so after that, we will plot the model to let you see what actually happened just now. Plot model. What did we do? Plot model. You have to put in your model, and then just to file. This is just an image that is embedded into this notebook.png. Okay, so from this image, you can know this is the input, that's layer 1, that's layer 2, and our output. So this is a very simple neural network with 2 layers. Okay, so next, from the slide yesterday, after every model, you need to have optimizer to optimize your model. So the optimizer that we imported just now is SGD, right? So we need to just call in SGD. It's very, very easy. So you name your optimizer as OPT and then SGD. Okay. Learning rate, you need to put in your learning rate. So what is this learning rate? We have already defined up just now. So learning rate equals to learning rate. Okay, you don't want to like define beforehand over here, right? You don't want to define here. You can just write 0.001 inside this parameter here. But to be safe, like in case you forget any hyperparameters, it is safe for us to just define beforehand. So you can just use all this variable name later on. So you have to call this optimizer. Okay, your optimizer is in. Okay, next we will compile the model, right? So you compile the model with the optimizer. Model.compile. Okay, compile your model. Okay, so we will have loss function to calculate the loss. So what loss function are we using? It is a categorical cross entropy. Okay, this is a loss function. There is a lot of loss function you can use, but then for today we will use this categorical cross entropy, and then we will have our optimizer, which is defined earlier, OPT, the SGD optimizer, and then we have a matrix here. We want to look at the accuracy. So what loss function is this? Usually, right, if we want to categorize the labels, we want to classify the labels into the labels, like we have a lot of categories, we will use this loss function called categorical cross entropy. So if you want to understand more about it, you can read here. They will explain on how it actually works, like the math behind it. So we will run this code, compile. Okay, we have already compiled our model. So after you have your model ready, we have already built the layer over here, the layer. And then we have already plot the model image. And then the optimizer, we compile the model with the loss function, optimizer, and also the accuracy. And then we will train the model now. So when we look at training model, every time we want to train a model means we are trying to fit the training data set into our model. So model.fit xtrain, comma, ytrain, we fit our data into the model. Okay, so then we will need to have the batch size. You need to define what is the batch size for this training thing, how much batch size you want to train on. So we have already defined beforehand our batch size, so just put in the variable. And then we have the epochs equals to training epochs. Training epochs. We have 10 training epochs just now. And then we have verbose is equal to 1. And then validation data. Okay, so every time you train a model, we need to have a validation data here. So what does this validation data do? Is that it will help you compare the accuracy between the training one and also with the validation data set. Okay, so S test and Y test. So what is this workbox? Later you will see. So let's say if you don't want to like have this variable, like I said just now, you can just change this into like 10, and this one can also be 10, like this. This is 100, right? So let's run. Okay, you can see epoch 1 is running. Okay, epoch 2 is running. You are now training the model. Epoch 3 is running. Then epoch 4 is running. Epoch 5. Epoch 6. Epoch 7. Epoch 8. Then we have epoch 9 and the last epoch, epoch 10. So you are training the model. Okay, is your model done training on your side? Yes, some of you is done. So you can see from this thing here, the first epoch, it has 600 over 600. 600 over 600. So what is this? This is the batch size. So you see we have a batch size of 100 here. So why is it 600 over here? So like I say, batch size is the amount of samples in each batch, right? So we have 600, we have 60,000 samples. Okay, but we want to have a batch size of 100 each. So 60,000 divided by 100. Okay, you will get 600 batches. So we have 600 batches with 100 samples each. So for each epoch, that means epoch is going through the data set for once, the entire data set for once. We will go through 600 batches over here, 600 batches over here, 600 batches over here, and so on. So what is this workbox? Workbox is nothing. Workbox is just this thing over here. You can see just now got arrow going through, right? This is the design for this thing. What design you want it to be. You can read more on the documentation online. Okay, so from here, you can see we got loss and then accuracy, validation loss, and validation accuracy. So let's say if you don't have this validation data set right here, right, you won't have this thing. Okay, you will only have this part. So from this thing, you can see, firstly, our accuracy is 0.3, then it will get better over time until 0.8. And then our validation accuracy is 0.88. Okay, so this is the test one. The validation is the test, and this is the training. So we will evaluate the model. So you have successfully trained your neural network over here. You want to test your model. That means we want to see the test loss and the test accuracy. You write here score, model, dot evaluate, S test, Y test. Okay, so you run this thing. Okay, so you can see the final score that we get is a loss of 44.95% and an accuracy score of 88.63%. So this is our model. So our model is 88.63% accurate. Okay, so you might, okay, up until here, do you have any questions? Do you have any questions? No? No. Okay, so until here, you can see that we have defined 10 epochs. So what will happen if you only run for one epoch? Anyone can answer if you only run for one epoch? What will happen? It means we don't have enough epoch for our neural network. We only got one epoch. What will happen to the model?
Then the accuracy won't be that high.
Yes, you are right. Correct, Mingli. So it is true. So if you only give one epoch to your model, you can see our accuracy is only 37%. So you have to give more epochs, but you cannot give too much of an epoch. You must give like the optimized level of epoch. So for our neural network here, right, we only got 2 layers. That means 2 hidden layers. So we will only just need like 10 epochs, like not much, not less, for it to get to like a satisfied percentage of accuracy, which is like 87%, which is actually quite high already. So what will happen if you give a lot of epoch to your model? So we can try that. Okay, can we try that? So you can see we have already run for 10 epochs here. So let's say we want to train the model again with another 10 epoch. So we will keep training it. So let's say if you train your model for like 20 epoch, 30 epoch, or 50 epochs, what will happen here is overfitting. You will overfit the model. Okay, the model will get overfitted. So we'll take a look here. You can run your overfitting train model here. Okay, you can see after another 10 epochs, right? Your model get better and better and better. Your validation is also getting better. That means it's a very, very good model right here. But then what will happen if you keep going and going and going for another few more epochs? The thing that will happen is your accuracy will get high, but then your validation accuracy will get lower. So what happens is when the accuracy for the training data set is high, it means that the model, the machine, is actually memorizing your training data set. It is trying to memorize. Oh, you keep, for example, if you give a child the same question over and over again, you will get familiarized with the question, right? Am I right? Like you read the same thing every day. You read the same thing for 1,000 times, for 2,000 times, for 3,000 times, for like 1,000,000 times. You will get really, really familiarized with the training data set. That means you are overfitted. That means you are saying that I can memorize this data set. Whatever example you give me from the data set that you train me on, I can immediately tell you this is a number 5, this is a number 10, this is number 6. But then what will happen is when you overfit your model and then you give your model something new to the machine. Okay, maybe another person like with very weird handwriting, he write a 5, and then you give this machine something he has never seen before, a new data set, then it might not be able to actually predict what digit is this because it is memorizing the training data set. That is what it means by the validation accuracy here. So if your accuracy of your model is really high, but your validation accuracy is very low, that means your machine is able to identify and predict the training data set very good. But then if you give your machine something new, it cannot tell you what it is because it got very used to understanding the training data set that you have given to your machine. So this is a problem in building a model. It can happen to all model. Overfitting is a problem. So there is a lot of ways you can deal with overfitting models by adjusting the values. For example, you can adjust the batch size. You can adjust the number of epochs. You can adjust a lot of these initialization values that we have already put in. So this is something very advanced. Like if you do more model, you can get really familiarized and experience in it. Then you might be able to adjust the value and avoid overfitting your model. Okay, so up until here, do you understand like what is overfitting? So can I say we have successfully built our first neural network? It is very easy, isn't it? You are done with today's neural network building model building. Are y'all okay? I mean, are y'all here with me? Hello? Is your model done building? You have already built your model?
Yeah.
Yeah, so are you happy you have your neural network model today? Is it really easy? Because in my opinion, I feel like this is much easier than the machine learning model that we built yesterday. What do you think? Yeah, okay. So you can see it right down here. We have left you some homework to do. So you can see just now the MNIST data set is a handwritten data digits, right? We have a lot of other data set you can try on from TensorFlow. You can go on and search TensorFlow data set. What data set can I deal with? We have a Japanese literature data set. Okay, maybe because we still have time left, we can look at this. So do you need a recap of today's notebook first before I move on to other part? Do you need like a recap? Okay, you need a recap. Okay. So what we did is we imported a library, and then we have this libraries for the neural network, and then we want to use this MNIST data set. So what we do is we import the data set and then split it into training and test data set. And then we have a look at our data set over here. What is inside our data set? How many samples do we have? How many train and test data set we have? And then after that, we want to take a look at our training image. What does it look like in the multi-dimensional array format? And then what is the label to it? And then we are ready. We have understood, oh, this is actually a number in our data set. We want to process our data set. So the first thing you do before you create your neural network is to flatten your image. Okay, so to flatten the image, you know that this is an image of 28 by 28 pixel. So we flatten the image into 784, which is 28 times 28. Okay, so after you flatten the image here, you change it into floating numbers because we want to standardize the value later. Because if you just leave it as integer, you will just get 0 for everything. Okay, so after that, you have flattened. We are trying to standardize your train and test data set. And then after you standardize, you can see we are left with numbers between 0 to 1. 0 to 1. Okay, and then our label is a digit 5. We don't want the machine to think there is a relationship between all our labels. 0 is smaller than 1, or 5 is bigger than 4, or 6 is smaller than 7, something like that. So we want to encode our labels, which is what we call one-hot encoding. Okay, so we have to identify, we have 10 categories, and then we convert them into this one-hot encoded vectors, which is an array like this. Okay, I'm sure you all understood this array part, this one-hot encoded part, because we have the image just now. Okay, and then after that, you just plot the picture. This is like a written code here. You just plot the image to have a look at the image you have. Oh, this is 5, this is 4, this is 1. This is actually what my data set look like. So just for example, before, if I didn't put in this image right here, you wouldn't know what the data set look like, right? You just import only. Oh, what does it look like? I don't know. But because I put in this, you have like an image to what this data set actually look like. It is like this. So like, let's say if you are dealing with the data, you want to have a look at your image. This is how you just plot it out and have a look at the image that you have. Okay. So next, we will have to define the network hyperparameter. Okay. And then you build your model. This model part is really easy. You just input, layers, and output and have your model ready. And then after your model is ready, you need to compile it with the loss function and also the optimizer. Okay, then your model is like completed. You can start to train it with the training data set. So after you train it, you can see, oh, our accuracy score is 88.6. So your model is ready. So this is what we do in the neural network model training. So do you have any questions? So far, so good?
Actually, I have a question.
Go on.
So for the loss function, I'm not too sure about the loss function.
Okay, sure. So the loss function here, let's have a look, yeah. Okay, loss function here is the categorical cross entropy loss function. Right, if you are not sure, you can come to here. This is the thing you can read here. It also have other activation function like the one I explained just now, softmax, and also the this is the one hot encoding thing, and the what do you call that, ReLU function. Oh no, they don't have ReLU function here. But to make it simple, categorical cross entropy loss function is a function for you to see the difference between two probability distribution. Usually it is used in the multi-class classification task. So let's say we have a tiger or a cat or an airplane. So with this loss function, it is able to see which probability based on the category. So whenever we have like categorical model that we want to build, right, we will use this cross entropy loss function. This is depend on the person itself. You can see here loss function. There is a lot of loss function you can use. Mean square error. Yeah, from yesterday's session, we use this mean square error loss function to actually calculate the difference between predicted and actual result. So whenever we talk about loss function, it is actually to look at how accurate your model is by calculating the difference between the predicted and the actual value. So we have a lot of loss function you can look at. So this is like a homework and reading you can look at. Yes.
I think I can further discuss on this part. Can I share the screen?
Yes, sure, go ahead.
Yeah, okay, so yeah. So as what I said yesterday, like you don't need to know too many theory because we're going to have cheat sheet for this entire model. Okay, so we start from loss function first, since that just our question is about loss function. So as what Sammy say, we have lots of loss function, okay? And then actually there's a way for you to know that which time to use which function. And for regression model, we use MSE. Yeah, because MSE is like, imagine there's a graph, right? MSE is like, this is the your predicted line. your best fit line, and then this one is the actual value. Yep. So this MSE is like basically is the distance between this actual value and the predicting line. Yep. So you can imagine like this. So this one is MSE. It's like a total difference between the actual value and the predicted value. So this is MSE. And then if you have a binary cross output classification, means that you're going to predict whether it's a cat or a dog, then you will use binary cross entropy. Yep. This one is like a law already. It's set already. Everyone is using this. Yep. And then for multi-class, right? So we use back the categorical cross entropy, or if you want, can use a softmax. Okay. But softmax is too advanced, not advanced. So I just left it here first. But normally people use categorical cross entropy. Like what just now Semi said, because you can see just now, if you still remember what Semi showed, is that for cat, probability is 0.23. For dog is 1, and then for the another animal, let's say it's a horse, and then it's 0.5. Okay, so it will compare to the original one, the actual number, which is 0.10. Okay, and then calculate how much difference is between the 0 and the 0.23. How much difference is the 1 and the 1? How much is the difference between 0 and 0.05? It's like this. It's just compare the difference between these two values, this different probability. Yeah, so basically just compare, the actual one and the predicted one. Yeah, so I will just come back to activation function. Okay, so there's a lot of activation function out there, but then trust me, like 90% of the settings is using ReLU for the inner layers. Yep, so for every inner layers, just use ReLU. And then for binary outcome, use sigmoid. For multi-class, use softmax. This is the law. Like everyone is using this. But if you have really read through all the documentation and found that, hey, actually this one is better than softmax, then yeah, feel free to come up with publication. Can come up with your your publication. But not most of them, they are using these three. And then for optimizer, right, you just add them an SDG for both regression or for both the classification. Yeah. The basic one is SDG and SGD, so it's stochastic gradient distance. And then for the advanced one is Adam actually. Adam is another optimizer which built on SGD. It's just an improved version of SGD. So you can feel free to use Adam. Yep. And then for the verbose is always 1, okay. And then for the batch size, okay. So for the batch size, actually, like there's some hints up for you, but then most of the time people are just using the mini batch mode, okay. This batch mode is actually like if let's say your data set is okay, I just add on here first, okay. This batch mode is actually like you set the batch size, okay. The batch size is equal to your data set size. Yeah. So this is what we call batch mode, okay. It's like you're not going to divide it into smaller batch. Instead, you just use the batch size equal to dataset size, and then but most of the time people is using this mini batch mode, okay. And then this the familiar numbers 64 until 512. Yep. And then this stochastic mode, right, is actually like you set your batch size equal to 1, okay. But then people seldom use this, okay, because you're already using the SGD. If you use back this batch size equal to 1, means that you're doing double work to check the same thing. So I won't go deep into stochastic SGD, but you just remember like most of the time people is using mini batch mode. And then for epoch, it's like, okay, it's just a kind of art. Like it's just your art. You can set any number. There's no true or false. Yeah. But then you have to remember that, okay, depends on data size, okay. If like just now the example, the data set size is small. You're not going to use the epoch with a big number, right? Because if you big number, then you will cause overfitting. And then normally number is below 500, okay, I would say. And then yeah, one more thing is like the more you set, the more waiting time you need, okay. Because I can imagine like some people really test the model use up to 5 hours, yeah, because they set the epoch. Yeah, but it's all come back to a data set itself, okay. Because this data set we're going to train is a simple one. It's just a black white mode, just a black white as grayscale one, and then the number is small, and then it's just 1 2 3 4 5 6 7 8 9 and 0. It's just this 10 number. It's considered as an easy data set. So small number of epoch is enough. But then imagine if you're going to determine like like Elon Musk Tesla car, you're going to train from whether there's a people, whether there's a tree, whether there's a way for you to drive. Yeah, you can use a small number of epoch because it's more complicated for data set. And it's also a it's a RGB one. It's like colorful one. Yeah. So it's a complicated data set. So you will have used a bigger number epoch. Yeah. So for this epoch, it's kind of art, but always remember you have to come back to see whether your data set need this amount of epoch or not. Yep. Yeah. So this is basically the conclusion. It's like the cheat sheet for your neural networks. Yep. And also the layers of the neurons is also a kind of art. You can set 2, you can set 3, you can set 10. Yeah, but it all come back to whether the data set really need this. Yeah, because the more neuron you have, the more mathematical function per neuron you have. Yeah, it's just like this. Each neuron we have their own mathematical function. Yeah. So come back to whether the data set really need it, but it's just a kind of art. Yep. So yeah, any question about this part? No.
No,
Okay.
no question.
Yep. So pass back to
Okay.
Sammy.
Okay. So we have done the MNIST data set on the handwritten digits. So I would like to show you there is also other MNIST data set. One of it, I find it really fun, which is the MNIST fashion data set. So this is also like the data set we had just now, except that this is a fashion one. So you have a t-shirt, trouser, pullover, dress, coat, shirt, sneaker, bag, and ankle boot. So for this one, right, you can go try and do it yourself. This is also similar to what we have did just now, but it is on the fashion data set like this. So in this fashion data set, you have to see whether this is a shoe or is it a dress or is it for a t-shirt or something like that. So the special thing is you can see this is an ankle boot, right? But this is like a shoe. This is a high heel, but they are all under the category of shoes. See, you have ankle boot, sneaker, coat, dress, and so on. Yes, this is something you can try out. And also, to anyone here, have you explored Kaggle before? Any of you here explored Kaggle before? Got? Got. Oh, Adam got? No others? No? No. So, like after this session, 3-day with us, you can actually go on to Kaggle. There's a lot of data set in Kaggle. You see they have face detection, avocado prices, machine learning, pandas, Python, deep learning, house prices, and so on. So you can click in here. So let's say you want to do deep learning. There's a lot of courses for you to do here. And then they have a lot of data set you can play around. Okay, you can play around with a lot of data set. So this is like something for you to explore. You can even see types of potato, mushroom, Airbnb stock prices. Okay, and then there's a lot of the data set you can use, import from this Kaggle thing. Okay, so TensorFlow. We have been talking about TensorFlow over and over again. So TensorFlow, can anyone tell me at least what is TensorFlow? Do you know what it is? I think you should know. What is TensorFlow?
A deep learning library.
Yes. Good. You are right, Adam. TensorFlow is a library developed by Google. So you will get surprised at how many companies and applications are actually using TensorFlow behind their technology, behind their application. So one of it is Airbnb, LinkedIn, Intel, Xiaomi, Uber. Then we have Twitter, Google, of course, and then we have Snapchat, Lenovo, Nvidia, PayPal, and so on. So this is the amount of the companies that is using TensorFlow behind their technology. So I would like to ask something, a brainstorming session. How do you think TensorFlow is applied in Airbnb? How do they apply TensorFlow in their app? Anyone here use Airbnb before? No, okay. Then do you know what is Airbnb? Yes, it's a platform for you to rent a place, right? Like a homestay one. Can you see my phone? It's like something like you can look at what houses you want to build or rent and so on. So this is Airbnb. So in Airbnb, we have a lot of pictures of the houses of the place that we want to rent, right? So we are dealing with what? We are dealing with images. So why do you need TensorFlow deep learning in this Airbnb app? Because we got a lot of images from the host. Okay, let's say the host, I want to host my house, right? I'll take picture of my kitchen. I'll take picture of my living room. I'll take picture of my toilet, I'll take picture of my swimming pool. Okay, then I'll just upload to this Airbnb application. Then it's just messy, you know. So Airbnb uses TensorFlow as the model, as their background model to help the app identify, oh, this is actually a toilet, this is a kitchen, this is a living room, this is a swimming pool. So it can categorize their host and the renting place into different categories. So it is not messy. It can help. So how is this done? It is done by image recognition. So we'll look at the image, or let's say if the model sees a stove or a plate or a dining table, then immediately it will know this is a kitchen or a dining room. And let's say if it sees a bed or a dresser or a clothing cabinet, then that must be a bedroom, right? So this is how the Airbnb company uses TensorFlow to help identify whether this image is in the toilet, or is it in the bedroom, or is it in the kitchen, or is it in the dining room. So this is how it is applied in Airbnb. Do you understand? Like, it's a very good knowledge to have, right? Isn't it? So when your friend tell you, oh, I went and ran an Airbnb, so maybe you can brag a bit about, yes, I know TensorFlow. I mean, Airbnb uses TensorFlow behind their application. So how do they use it? They help to identify different objects inside the image and then classify it as a kitchen, or is it something, or something. This is how it is used. So you can actually look at other companies that uses TensorFlow by yourself. Yes, so this is one of it, the use case. Okay, so for today's session, I think it is up until here.